Morning, everyone. Welcome to Soil Science Seminar. And for me, it's still a strange world. I have a real audience here. I know there's an audience out looking somewhere else too. Anyway, good morning. I'm delighted to say that this week's speaker is Richard Roth. Dr. Roth is an assistant professor in the department, so he's been here a very short time. Backing up further, he's a native of Illinois. I believe it's Divernon, Illinois, south of Springfield on Interstate 55. Earned his baccalaureate and his master's degree at Illinois State University. He then went to Purdue University, where he earned his PhD with Solomon Armstrong, looking at cereal rye. But he has but I think he's going to tell us a little bit about that. From there, he stayed at Purdue, where he did a postdoc for a year, and then from there he moved to University of Georgia, became an assistant professor, and then I'm delighted to say he decided being an assistant professor at Iowa State sounded better than being one in Georgia. So thank you for being here, Richard, and look forward to hearing your presentation.
Thank you. All right, well, thank you to everybody that's here and online. So the title of my presentation today is Impacts of Cereal Rye on Midwestern Corn and Soybean Agroecosystems. I'm going to talk about that, but the first thing I'm going to do is kind of go a little bit deeper than what Dr. Burris just did. For those that don't know me, or maybe have seen me but don't know, never met. Okay, so I need to advance my slides. Okay, so as he said, I grew up in Illinois, just south of Springfield, which is the star on the map there. It's a little town called Divernon. You'll never hear of it ever, except if you drive past it on Interstate 55 and you look off to your left. If you're driving south and you look off to your left-hand side, you'll see this giant grain elevator there, and you'll think, oh my goodness, that's a huge operation. And then if you were to look into it a little bit more, you would find out it's one person that farms about 100,000 acres every year. And so he has a huge operation there. It's really neat to see even on Google Maps. Okay. Like you said, I did my bachelor's and my master's at Illinois State University, which is in Normal, Illinois. I just wanted to share some pictures of my time while I was there. I really focused on conservation cropping systems during my master's. The other thing that I decided to do is from each state that I've lived in is give you maybe the most memorable or coolest or best thing that has happened to me. And so while I was in Illinois, here it is. I burnt down a truck while I was doing some research. So unfortunately, all of our samples, all of our grain samples were in the bed of that truck. Everything was lost. It happens, you learn and you live, right? From there, as Dr. Burris mentioned, I moved to Indiana, to Purdue, where I worked with Solomon Armstrong. I continued to work with Solomon Armstrong. He was actually my master's advisor as well. And while I was there, I got a lot of good experience working in extension, doing research. So I did some controlled environment research, which is, you can see there where I'm looking at the plants and the pots. I did some lab work as well. And I also did some teaching while I was there. But the best thing that happened to me in Indiana is that I met my wife while we were at Purdue, and we got married. And while I'm on this topic, I'll give her a shout out. If anybody needs a veterinarian, she works up in Roland, and she'll be back to work here in about a month. And so she does large and small animal medicine. So after finishing my PhD at Purdue and spending a year as a postdoc, I joined University of Georgia as an assistant professor in their, I like to say, everything but cotton and peanut specialist. And if you don't know anything about the South is not the place to work on anything that's not cotton and peanuts. And the other thing is that they have a bunch of people who grow very small acreages of very niche crops. And so on any given day while I was down there, I could go from a phone call about corn or soybeans to one about what herbicides do I use for sunflowers, what seeding rate do I use for sesame, small grains questions, things like that, right? So I gained a lot of experience. The other thing that I learned while I was down there, I had never planted or harvested or fertilized or sprayed herbicides on my own crop before. And while I was down there, I had to do every single bit of farm operation from field prep all the way through harvest. And I'll be honest with you, the equipment that I had down there was, it had all the bells and whistles on it, so I got a crash course. But it was good because now I'm able to better understand, what farmers are dealing with. I did a lot of extension while I was down there, planned a lot of meetings. Luckily here, I don't have to do that. But the best thing that happened to me while in Georgia is Iowa State, right? And so when I left Georgia, I joined Iowa State back in September. I realized today that I have been terrible at taking pictures since I've gotten here back in September. So I don't actually have any pictures of anything I've done since I got here. But my role here is I have an extension and research role, so 60% extension, 40% research. This past winter, I've been all around the state talking at different extension events. But that's all good and great. But best thing that has happened to me since I've been in Iowa is we had our little baby girl. Now wait, I've learned from a couple meetings that if you bring up a baby, it'll fill some time, right? So I've got some more pictures. Okay. So that's my daughter, Elowen. She was born on February 16th. So she's about a little under 6 weeks old now. And 1A, 1B, getting married and having my baby, best things that have ever happened, right? Okay, so that is my journey to Iowa State. While I'm here at Iowa State, I'm going to focus mainly on nitrogen and sulfur management and cycling and agro-ecosystems, okay? All right, so let's actually talk about some research, and I'll get through whatever I can here. If I don't make it through it all, it's okay. This is, I would say, a modified version of what I've been delivering to farmers across the state. So I think we all probably know that most farmers operate with some things in mind, right? They want to maximize their production and their profit, and they want to maximize their input use efficiency. And whether they realize it or not, by doing that, they also help hopefully minimize the environmental degradation of their systems. And this is important because the black dotted line here is population, right? Population has been increasing, it's going to continue to increase. So to meet that growing population, we have to increase food production on the same or less land, right? We're not getting any more land, but it's possible that we're going to lose some. And so we need to be able to keep up with that. And that's going to require a whole myriad of things, right? But a couple of key ones are increases in better genetics, which we get genetic gain every year, which is good. But we're probably also going to have to increase input use. And if you think about Iowa and what we grow here being a lot of corn, that's primarily going to come in the form of nitrogen. And so you look at nitrogen use over time, over the last 70 years or so. On the left-hand side of the screen, we have inorganic fertilizers, and on the right-hand side of the screen, we have manure. You can see that big red area on the map is basically Iowa, right? We've continued to increase nitrogen use. And if we look kind of on a state level here, as the colors get lighter, it's actually indicating greater nitrogen use, so greater tonnage of nitrogen being used in a given year. And you can see that we've basically, over the past 70 years, increased nitrogen use in every single county in the state, which again makes sense because of what we grow, the change in genetics over that time frame, right? The change in availability of fertilizers. And so it just makes sense. So then if we think about nitrogen use efficiency, and there's dozens of definitions for nitrogen use efficiency, okay? The one that I'm going to use, I think technically, if you were going to really dig into it, it's called agronomic efficiency, okay? And it's essentially comparing the yield of a fertilized crop to an unfertilized crop, and then dividing that by the amount of fertilizer applied to the system. And essentially what that gives you is the percentage of nitrogen that actually made it into the crop. Okay, so in the United States, our average nitrogen use efficiency is about 68%, meaning that about 70% of every pound of nitrogen that we apply to the farm makes it into the crop. And so we expect that number to kind of go up over the next 25 years or so, but not a whole lot. We're never going to reach 100%, obviously. But we've kind of stayed, if you look at the figure here, we've kind of stayed pretty static around that 70% for the last 25 years or so. Okay. Now, on a state by state level basis, if you look at this map, if you look at Iowa, what this is telling us is basically the change in nitrogen use efficiency per year over a given time frame. You can see that over the past 50 years, Iowa, we have been consistently increasing nitrogen use efficiency, but over the past 15 years or so, it's been at a slightly slower rate than it had been in the past. Now, if you couple that with the fact that we're sitting in one of the most heavily tile drained landscapes in the world, what you end up with is these water quality issues that I'm sure that we've all heard of. They make headline news every single year. There's been lawsuits over it down in Des Moines. There was a big one with Des Moines Waterworks. And it's because if you look at this map, this is a map of the states that contribute the majority of nutrients to the Gulf of Mexico, to the Mississippi River, which feeds the Gulf of Mexico. And Iowa is number one by far for nitrogen contributions. Number two is Illinois. Number three is Indiana. But the other problem is that we also contribute a lot of phosphorus to the system as well. And so the combination of those two is what really causes the issues in the Gulf of Mexico. So the dead zone, hopefully we've all heard of the dead zone, that area, the area where basically nothing can live, right? Because of the algae blooms that occur. And then when the algae dies, the microbes feed on the biomass, and they respire, they use the oxygen, and it basically becomes oxygen depleted, right? And so the real problem is that for us as the agricultural community, right, is that we are basically the only industry that's not regulated, right, where they don't measure direct losses of these nutrients. And so what that means is that they basically say anything that they didn't measure that they find down there, they contribute to some form of agriculture, right? And so for nitrogen, it's about 70% of the total nitrogen load comes from some form of agriculture. And so that's not great, and we get blamed a lot. It's not necessarily that we're doing things wrong. It's that we can't control a lot of factors that lead to these environmental losses. So back in 2008, the EPA got together and they created the Gulf Hypoxia Task Force that said we need to reduce nitrogen loads by 40% and phosphorus loads by 45% to the Gulf of Mexico. And very simple explanation is they kind of looked at this map right here, and they identified the 13 states that contribute the greatest amount of nutrients to the Gulf of Mexico. And they said that basically you guys need to develop state level strategies to help reduce these nutrient loads. And for Iowa, it's called the Iowa Nutrient Reduction Strategy. This is an older version of it. It's updated every so often. But basically what it is, there's a lot to it, right? But what I'm showing you is there's a list in there of practices that we can implement on our farms to help reduce nutrient losses. And here, this figure that I'm showing is specific to nitrogen losses. So you can kind of break it down into two different categories: edge of field practices, so things like wetlands and bioreactors and buffer strips, and then infield practices, which is basically 4R management, so right place, right source, right time, and right rate, and then increasing cropping intensity. And so what I mean by that is extending the period of time in a given year where we have roots in the ground, right? And if you think about how we do that, there's really a couple ways. Number one is add a small grain in our current rotations. Number one is to add a small grain to our rotations. And like I said, I've been all around the state this year, and I ask every time I talk, I say, is there anybody that grows wheat or any other small grain in here or something other than a cover crop? And I think in the, I don't know, 15 times that I've done this, I think I've had maybe 3 hands. So we don't have a lot of small grain production in the state. So the other way is to use a cover crop, which introduces that living root into the system. We just don't harvest it for as a commodity, right? So I'm going to specifically focus on cereal rye for 2 reasons. Number one, it's like 85% of the cover crops grown in the United States, and number two, it is the cover crop that is most heavily highlighted in basically all state nutrient reduction strategies. Okay. So when I talk to farmers about cover crop systems and what makes them, I guess, high performing, I guess you can have your own definition of what that means, but I tell them that the factors that we try to think about in it is the oldest use of cover crops, right, is to prevent soil erosion. And we know that they do that pretty well, right? Number two is this idea of reducing nutrient losses. Number three is potentially promoting nutrient use efficiency or nutrient cycling. And number four is if we're going to have these systems, we need to be able to produce cash crop yields at a competitive level as if we didn't have that cover crop in the system. Okay. So really, when you break it down, you've got an environmental component and an agronomic component. Okay. I'm going to start with the environmental side of things. Back in 2014, when I started my master's degree at Illinois State University, we implemented this study on a farmer's field. They basically gave us this 25-acre block. They said, do what you want with it. So we tiled it very intensively. So we had 15 individually drained fields here. They're each about 1.5 acres. The red lines are the tile laterals that run within that plot area. So we have 3 of them. They're spaced 45 feet apart. The blue lines that you see on there, the thick blue lines, those are our border tiles to help reduce any lateral movement of water. And then the yellow boxes that you see there is our automated tile monitoring stations. So we have a sampler that goes down into a controlled drainage structure and actually pulls water samples from there. We also have a velocity sensor in there so we can tell how fast the water is moving. It also has a pressure transducer so we can determine how the level of the water in there as well. And in this system, we wanted to test a couple hypotheses. Number one is does transitioning the majority of your nitrogen application from the fall to the spring, does that reduce nutrient loads? And then in both systems, a fall dominated system and a spring dominated system, is adding cereal rye help reduce the nutrient loads? Okay. So when I say fall dominated, we had 80% of the nitrogen in the fall, as in hydrous ammonia and DAP. And then the rest in the spring at side dress, as in hydrous. And then in the spring system, it was about 20% or so, 15 to 20% is what we got from DAP. So that was in the fall. and then the rest was applied at side dress as anhydrous ammonia. Okay, so this is a look at how the cover crops, we'll say, performed in this system. So on the left, we have cover crop biomass. On the right, we have cover crop nitrogen uptake. And I apologize for the mix in units here, but this is what I show to farmers. So farmers need to have it in bushels pounds per acre and things like that. So you can see over the time frame that I'm going to show you from 2015 to 2019, we had a range in cover crop biomass from 500 kilograms per hectare all the way to about 2,200 kilograms per hectare. On average, we were somewhere around about 13 to 1,400 kilograms per hectare. And then on nitrogen uptake, we had things below 20 kilograms per hectare, all the way up to 85 or so kilograms per hectare, with an average around 45 kilograms per hectare, 40 pounds to the acre. Okay. So let's look at the water now. So on this figure, on the left-hand axis is rainfall in inches. That's the blue bars on the graph. On the right-hand side, we have flow-weighted nitrate in milligrams per liter. And that is the black and the green, which the black is no cover crop, the green is cover crop. The reason I'm showing it as only that and not the system separated is because we didn't actually see any difference between fall and spring systems with or without cover crops. And I'll show you that in a second. The red dotted line on this is our EPA drinking water standard of 10 parts per million nitrate. So I suppose I'm not necessarily saying that we need to keep our tile water below that level, right? But the thing to understand is that that red bar that's on there, that 10 parts per million, was the cause of the lawsuits. The concentration of nitrate in the water got so high. The black bars on the x-axis, basically those represent the time frame where the cover crop is not growing. So after we've already terminated it, and what you'll notice is that even in those time frames where the cover crop is not actively growing, obviously the corn or the soybeans is growing during that time frame, right? But even then, we still see a reduction relative to the control system. And so at that point in time, there really is no difference between the two systems other than the residue, the decomposing residue in the system. Okay, keep that in mind. Okay, so the other way to look at it is total amount of nitrogen lost. So here it is broken out. Like I said, we did not see any significant differences between fall and spring nitrogen. And in fact, in our system over the time frame, cumulatively, we've seen more nitrogen leave the spring system than we have the fall system. But where we added the cover crop, we see about almost a 50% reduction in nitrate loading. And one explanation to help with this is if we look at the total inorganic nitrogen in the soil profile at planting. And so across the top axis, we have total inorganic nitrogen. Across the y-axis, we have depth. So as you go down, you're getting deeper into the soil. And again, we didn't see any differences between the fall or the spring system. And so you can see where we had the cereal rye, we had less total inorganic nitrogen in the system. And so that kind of helps start to explain why we would see less losses there. Okay, so we also looked at nitrous oxide emissions from that same in that same experiment in 2017 and 2018. So one corn year, one soybean year. And what we saw, so in the corn year, we saw a pretty significant reduction in total nitrogen losses. So nitrate and N2O. N2O is the yellow, nitrate is so air is the yellow, water is the red. But we saw a slight increase in gas emissions for the cereal rice system in the corn year. In the soybean year, we saw a slight reduction in total nitrogen losses, but we saw a significant increase in N2O emissions with cereal rye relative to our control. And so what we wanted to do with this is there is a term called environmental damage cost. And so basically it is a way to put a dollar value to nitrate losses or N2O emissions. And so we did that, and in the 2017, the environmental damage cost we had a significant decrease in environmental damage costs where we had the cover crop versus where we did not. And I'm not going to talk about the zero control right now. But in 2018, in the soybean year, it was still less, but the difference was not significant. And you can see that there was, again, we increased N2O emissions, so there was a much greater proportion of the environmental damage costs made up from the N2O emissions. So when you look at it on average, okay, across the rotation, so corn and soybeans, as far as just nitrogen losses, we had about a 50% reduction in total nitrogen losses, which also translated to about a 50% reduction in environmental damage costs. The thing that we were concerned with here that another paper had found was they actually saw that the increase in N2O emissions, so the increased environmental damage costs that they saw from increased N2O emissions actually offset the benefit that they got from reductions in nitrate loading. But in our case, we actually saw basically the exact opposite of what they saw, is that even though we increased N2O emissions, it didn't offset the benefit from the nitrate reductions. Okay, so that was at the small scale where we had a lot of control. We had really no farmer influence other than the farmer telling us that he was not going to account for the nitrogen in the DAP, so we had to up our nitrogen rates. But what we want to know was if we scale up to a watershed where we don't have basically any control and a lot of farmer influence, do we see the same thing? And so we found two watersheds, which are probably 5 miles from that other, from the plot site that I just showed you. We started this trial back in 2014 as well. It's still going. It has the same experimental design still at this time. So the blue watershed is 700 acres. We don't put any cover crops out there. In fact, we pay the farmers in that watershed not to cover crop. In the red watershed, we pay the farmers to put a cover crop out there, and we get about 50% coverage each year. So before corn, they're generally growing an oat radish mix, and before soybeans, they're generally growing a cereal rye radish mix. That's what they chose to grow. We did not influence that. That's what they wanted to do. So we paid for the cover crop to be flown on in late August, early September, and then we paid for the termination costs as well. We have the same water monitoring systems at the outlets of each watershed. And so what we've seen over the past 5 years or so is an average reduction in nitrate load in pounds per 1,000 gallons per day of about 31%. So why am I not showing you the first couple of years? Number one, because this is the nice fancy graph that I have. But number two, because in the first couple of years, and if you ever see Matt Helmers talk about his watershed project, he'll say the exact same thing. At that scale, you don't see any change. It takes a couple of years for the change to actually occur. So for the first, I would say 2 years, so 2014, 2015, we actually saw a greater amount of nitrate leaving the system from where we had the cover crop. That's for two reasons. Number one, because we weren't scaling it on a per acre basis. If you scaled it on a per acre basis, they were about equal. Yeah, so anyway, about the third year is where we started to see a small reduction occur, and then over time, it's just kind of built. And what I'll point out is that in our Iowa nutrient reduction strategy, they say that if you use a rye cover crop, you'll get about a 31% reduction in nitrate. So we're right in line with kind of what the science review teams are saying. For phosphorus concentrations through the tile, this is dissolved reactive phosphorus, which is say the more environmentally damaging form of phosphorus. We don't see any differences. This kind of makes sense because we don't really lose a lot of phosphorus through the tile system. You'll notice that the units here are in micrograms per liter, so very small amounts, right? But what we realized over time was that a lot of the water leaving these watersheds is through overland flow. And so you can see how fast that water is moving through that system. This was after maybe a 2-inch rainfall, okay? So we have a lot of water moving overland and we were missing it. And so we actually set up systems in these culverts to measure the amount of water leaving the system overland and also pull samples from that. And I'll show you from like when we very first started, this is an example of about 1.5 inch rainfall event. And so it can be a little bit misleading. So on the left, we have discharge. On the right, we have nitrate load in pounds. So on the discharge side, it can be a little bit misleading because it says there that we're actually losing more water from our treatment watershed, but we have to remember that it's 400 acres larger than our control watershed. So if you do it on a per acre basis, we actually we're having less discharge from our treatment watershed overland, actually total. And then if you look at nitrate loads, we cut it about in half, okay? And so the interesting thing that we found here was that at least in these watersheds, about 76% of the discharge was overland flow versus tile. Okay, so that's interesting finding. So environmentally, I think that we're doing pretty good. I think maybe we could question the gas emission portion of things, but it is what it is. So agronomically, and I'll kind of go through this relatively quick here. When we look at the impact of cereal rye on soybeans, so this is going back to the first plot study that I showed. We didn't see a significant influence on soybeans. For farmers, they care that it was a 3.5% difference, but for us, we didn't see a significant difference. For corn, we did see a significant decrease following cereal rye, about 13%, and that's over a 3-year average. And so we wanted to try to dig into that yield decrease in corn that we were seeing. So we sampled corn at different growth stages, V6, V12, VT, R6, and we measured total nitrogen within it. So on the left-hand side, we have nitrogen content in kilograms per hectare. And at R6, we saw a 22% decrease in the total nitrogen uptake where we had cereal rye versus where we didn't, which equates to about 60 pounds per acre on average. But the thing I want to highlight here is that you see that gap start to form around the V12 growth stage. Okay, so if I can get to it, that'll come back up. Okay. The other thing that we looked at was nitrogen use efficiency, and we saw a significant decrease in nitrogen use efficiency of about 31%. So keep in mind. Remember, when I talk about nitrogen use efficiency, I'm saying basically the proportion of nitrogen that made it into the crop. So we basically dropped from 70% of every pound to 40% of every pound. So we wanted to know if this was just us or if other people are seeing this. So during my PhD, I went across the Midwest and I found data from all the sites that you can see highlighted on the map. So I ended up with 430 paired observations for corn. So by that, I mean a plot with cereal rye and a plot without cereal rye. And it's a combination of on-farm and research data. And what I found was that on average, there was about a 6 to 6.5% decrease for both crops following cereal rye, which is interesting because most people would tell you that there's not much of an effect on soybeans after cereal rye, but that's not what we're seeing kind of across the region. So to highlight the nutrient reduction strategy again, they say if you use cereal rye, you're going to lose 6% corn yield. So right in line with what, again, with what the review team is saying. There's a recent paper out of Illinois that used remote sensing to evaluate crop yields with and without cereal rye. And they basically came to a conclusion that corn was having about a 5.5% reduction and soybeans 3.5%. So not far off from what I found. Here in Iowa, John Sawyer saw the same thing. He saw an average 5% reduction in corn yields following cereal rye at varying nitrogen rates. So he was never really able to make up to close the yield gap regardless of nitrogen rate. If we take that big data set that I showed and we break down to just Iowa, this is what it looks like. This is 146 out of those 430 site years. So 45% of the time we had a loss, but on average it was a 2.1 bushel decrease in yield. What I'll highlight here is that so the green bars, which is cereal rye biomass, the average biomass is only 560 pounds to the acre, which is very small cereal rye. And of the trials, of the 146, only 42 of them were over 500 pounds to the acre, and only 24 of them were over 1,000 pounds to the acre. So what that means is the majority of the cover crop was basically 6 inches tall or less. The other thing that I would highlight here is that one interesting thing that I kind of take away from this is that the level of biomass does not necessarily correlate to change in yield. So if you look at the right-hand side of the graph, you'll see some cereal rye biomasses even up to about like 2,700 pounds to the acre, where we're getting 20 to 25 bushel per acre yield increases. But then if you look at the left-hand side of the graph, we have biomasses that are as low as 1 to 200 pounds to the acre, and we're getting 40, 50 bushel decreases, right? If I had to guess, it is because this biomass that I'm talking about is only above ground biomass. So it's not taking into account anything that's below ground. Apparently I deleted something in here. Anyway, conventional thinking would tell you as the system matures that effect goes away. The Iowa data spanned from first year implementation to 15th year, and you can see that kind of regardless of the age of the system, there's always that risk associated with it. Oh, here's soybeans. Soybeans, same exact story. Okay, I'm gonna skip this one, but just know that the economics don't play out well, and that your average net returns are generally negative, even up to 9 years. You don't have a very good job of breaking even. If you wanted to break even, here's the payments that you would need based on the age of the system. And these payments are higher than current equip payments. I'm happy to share this with anybody that wants to see it, but here's basically that payment that you would need to get versus current payments that are out there. So equip, insurance discount, an average carbon market payment, or out in the Chesapeake Bay, they do nutrient trading. So that's what the bottom right-hand one looks like. Long story short, current payments don't stack up to what we actually need. And that's not, I found that, but this is another paper that saw the same thing. And then Alejandro Plastina, who is in ag econ here, saw the exact same thing when he did his math. So what's happening? How much time do I have? A couple minutes. Okay, so what's happening? I think that we have this tug of war going on. There's multiple things happening, but I think one big thing that's happening is that we have a tug of war going on between our corn crop and our microbiome over the nitrogen in the system. And so to highlight that, when I was doing my PhD, I was interested in looking at the release of nitrogen from cereal biomass back to the soil system, and then the soil pool that it ends up in. So this is a look at the roots and shoot biomass combined. And it's basically it's released into different pools over time. So the white pool is unrecovered nitrogen. So I have to say unrecovered because we didn't measure gas losses in this system. So it could, in theory, because it was a closed system, there was no leaching. So it could, in theory, either be still in the solid biomass or it could have been lost through gas losses. The dark gray is nitrogen that was in the organic nitrogen pool. The black portion of the bars is the microbial biomass nitrogen. And then the green is inorganic nitrogen. Okay. So what you'll notice is that basically the two things I'd like to highlight here is that the majority of our release to the soil occurred between what would be our V6 corn growth stage in the field and our VT growth stage. And that was about a 46% increase in nitrogen release during that time frame. But what you'll notice is that even though a pretty significant portion, so 67% of the total nitrogen made its way into the soil, only about 14% actually became plant available at any point during this incubation. And that was with our average seed-to-N ratio was 23:1. So that number is below the book value, right, for mineralization. But we didn't see a huge increase in inorganic nitrogen coming from that residue. Okay, so this is a very busy slide, but I'm going to go through it. This is basically looking at that figure that I just showed in a different way. So the dotted line on the top is the organic nitrogen pool. Solid black is inorganic. The dashed line at the bottom is the microbial biomass pool. And so you'll notice here up front, so between basically when we terminate the cereal rye and the V3 growth stage, is when we get most of the decomposition or the sizing of the residue going on, okay? So they see that all the time in litter bag studies, which is the figure on the top. That drastic decline in the curves is basically showing a rapid breakdown of the residue, okay? On the bottom, it's the exact same thing. It came from a litter bag study. The dashed lines are basically looking at kilograms of biomass decomposed or broken down, released from the bags per day. And you'll notice that they peak at around V3. So that's important because the biomass has to be sized, broken down before it can be cycled by the microbiome, right? So then if we look at the V6 growth stage, that's actually where we see soil beta glucosidase activity peak. So I'm not a microbiologist, but my interpretation of this is that from the person who did it, that was in my lab, is that soil beta glucose, you know what I'm saying? Basically, is a representation of carbon cycling by the microbiome. Okay, so essentially we see it peak at V6, so we're seeing peak carbon cycling at V6. Okay, so obviously the residue, the carbon has to be cycled before the nitrogen can be released. And so here at about VT is actually where we see soil urease activity peak. So urease is, again, I'm not a microbiologist, but the simple explanation that was given to me is that that is basically helping in the conversion of organic, organic to inorganic nitrogen, essentially. And then during this time frame, so VT to R6 is when we see soil inorganic nitrogen peak in the system as well. And so I think it helps explain kind of what's going on. I think it helps with my assumption that we have some microbial stuff going on here. I think the important thing to remember is that in order for the microbes to cycle cycle carbon, they need nitrogen, right? And so during this time frame where it's cycling the most nitrogen or the most carbon, it's also utilizing the most nitrogen from the soil profile. So that helps explain, and that's right at a time where we see the highest demand by the corn. So here's my very simple visual model that helps farmers. I don't show that slide to farmers. So I tell them, okay, we see peak cereal rye decomposition or breakdown around V3, right? And then we see peak microbial demand for nitrogen around V6, right? So that's when it's cycling the most carbon. And if you look at the nitrogen demand curve for corn, it's a very simplified, right? But there's a huge overlap in all three of these curves, which really, I think, helps start explain some of what's going on. Now, I told you that what I showed you earlier, that was in a lab setting and incubation. We did the same thing in the field, basically to look at utilization of cereal rye nitrogen. And we found about 10% on average between corn and soybeans. Okay, I'm gonna
It's
stop.
probably a good time to take
I'm
questions.
gonna stop and I'll take questions, and I have slides. If you have a question, hopefully I can answer it. Okay. Questions in the room? Yeah, go ahead.
In the infancy of no-till adoption, we saw slides similar to what you had. We had the distribution of profit versus loss with. So when you're talking to farmers and you have farmers out there that swear at you that, yes, this system works. How do you deal with it? There's art along with science in terms of making cover crops work.
Yeah, so for those online, if you couldn't hear, the question was, how do I explain basically the economic slides that I showed that say that cereal rye doesn't work? First of all, I suppose I was pretty negative here. I'm not against cereal or cover crops, right? Everybody has their own system, and I think the biggest thing is that, so in the economics that I looked at, I didn't take into account things like different nitrogen management or different practices on farm. So that's one thing. I get a lot of farmers every time I share this that argue with me. Not argue with me. We have a discussion, and I tell them if it's working for you and you're happy, that's all that matters. But the other thing I tend to ask people a lot is, do you have a spot on your farm where you don't have cereal rye so that you know what production would be like without it? And 99.9% of the time, the answer is no. And so my response to them is, so you don't, it is working for you, but you don't actually know what it could be without it. And a lot of times the response is, I don't really care. So I think it really depends on what is the reason why people are using the cover crops in the first place, right? If they're using it to build their soil, to, make sure that their grandkids can farm, I think that they care less about the economics, to be honest with you, as long as it's working for them. For the people who don't do it for that reason, right? Who are doing it because it's been pushed on them, or they know that they can get a payment from an RCS or whatever. It's a lot harder to rationalize, to be honest with you. Yeah, I mean, honestly, I've seen so many crazy systems where people are like, it works, and then, yeah, I don't know. A lot of times they're doing really crazy things that it's not feasible for every farmer to do. So there's one farmer in Indiana who swears by his system, says it works. I'll show you his economics. But what he doesn't, and he claims that it works because he can reduce phosphorus and potassium applications. But what he doesn't tell you is that every time he gets a field, the first thing he does is put on 10 tons of manure, right? So yes, it kind of makes sense that you could probably reduce phosphorus and potassium applications, especially in those soils that are already high in phosphorus and potassium. So I don't know. That didn't really answer your question.
Oh, that's good.
Well, now I have two questions.
Okay.
The first one is, couldn't it be that those farmers who are ignoring the economic costs that you mentioned have decided that they no longer want to externalize the cost on society of farming the way that they have been doing it in the past. They're willing to give up some of their profits so that they don't have the responsibility to force the rest of us to pay for it.
Yeah, so the question or the comment / question was, is it possible that the farmers who are operating under, that are doing it, let's say for the right reasons, are doing it because they don't want to pass on the externalities to society, basically? Yes, honestly, that's what most of them say.
I'm glad to hear that
Yeah.
that some of them have adopted that.
Absolutely. There's pretty large contingent, I would say.
And to me, that's something to celebrate.
Yeah.
Okay, my question has to do with the nitrogen use efficiency.
Uh-huh.
In the equation you showed us,
Mhm.
you had in the numerator yield differences divided by nitrogen.
Mhm.
But you interpreted this to be the percentage of nitrogen that was actually taken up by the crop, which is a different calculation that for nitrogen use efficiency, the difference between agronomic use efficiency and uptake use efficiency. Now, I could see that there's a relationship if nitrogen uptake perfectly tracked yield. However, the slide that you showed us, John Sawyer's data showed it's not a linear relationship. It's actually quite a curvilinear, nonlinear relationship. So could you talk about the discrepancy in those differences between?
Yeah, actually, I think so. Yes, I will. So, it's because I had the wrong equation up there. So, yeah. So what I showed was what we would call agronomic efficiency. And what I described, I don't remember the exact term for it, but basically what I described would be, instead of yield, you would do plant total nitrogen.
Yeah.
Yeah. And I had that, I pulled that from I have different slide sets that have different equations, and I got that wrong. Good.
I have a follow-up. Well, first of all, thanks for the presentation, Richard. It's cool to see all this work you've done over the few years before coming to Iowa State, and neat to hear about, getting out the state and talking to farmers in Iowa. I have a follow-up question on the nitrogen use efficiency. So I think you even alluded to this, that maybe the agronomic efficiency isn't the best one. Have you considered other measurements, especially in light of, I think whether or not you use the nitrogen uptake or the yield
Mhm.
in that calculated equation, you'll probably end up with a negative number or less, or a lower number for the cover crop system.
Mhm.
Have you considered using like the system's nitrogen use efficiency? Because you have the nitrogen loss measurements. I think you could even use N2O in that.
The simple answer is no, I haven't, but that's a good idea. No, I mean, we mainly focused on the agronomic efficiency. But we looked at agronomic efficiency, and then the people say nitrogen use efficiency, the uptake efficiency, basically. But really the plant nitrogen over fertilizer nitrogen is actually a combination of nitrogen uptake efficiency multiplied by nitrogen utilization efficiency is actually what it is. But no, I haven't, but that's a good thought. We haven't looked at doing that. So you're correct. Neither one of those is necessarily the best way to do it, because they kind of ignore like inherent soil nitrogen.
Yeah, and losses. Satirius had a student, I think he published the paper in 2018 that uses a bit of modeling, but I think data as well in that paper to incorporate losses into that equation too.
Yeah, I mean, we have the data to do it. We haven't done it. I'll be honest with you, I did that like that was from like 20 when I was a master's student.
Yeah.
And so I don't necessarily work with the data a lot anymore. I just kind of share what we have. But those are good thoughts, and I can go back and do that. Yeah.
One more question, but I see it back here. Go ahead.
Go ahead.
Thank you for your presentation. And I'm not very familiar with the agronomy field in USA because I'm from out of state. But if the farmers really pursue the economic profits, do you think the carbon credit or carbon market, this kind of thing can be sufficient to make farmer cultivate cover crops or use cover crops?
Okay, so for those online, the question was for the farmers who are worried about basically the economic losses that I showed is the carbon market the answer basically to make up for that. So I kind of went over it, like I skipped over it a little bit. And again, this is based on the data that I have, right? But the average carbon credit payment, and I used 15 megagrams, or I used $4.80 per hectare per year, basically. So that what that equals is like a $15 payment multiplied by the actual carbon that transitions into soil carbon from cereal rye. The short answer, I think, is that based on what I've seen, no, because the average payment is like $20 per acre. However, and again, I'm not a carbon market expert. However, when they first started, they were basically judging it on like performance, like actually doing the practice, and like actually building carbon in the soil. And I think there's now some that are transitioning and paying it based on what your CI score is, or your carbon intensity score on your farm. And so in that sense, it's possible that having these practices actually can get you, I don't know that it gets you more of a payment, but it gets you probably a more consistent payment, because it's not paying based on actually building carbon, it's paying on you're doing practices that help capture carbon, basically, or reduce carbon emissions. So like the thought is when you use cover crops, you're going to hopefully not till. So you're reducing, fuel use and things like that. It's a good question. The answer is nobody knows, because the carbon markets are like the Wild West right now, and they're not regulated. There's no standardization, and it's really tough, even as a farmer, to decide which one you want to be in. And so, like when I've had farmers talk to me about it, they're like, I don't. What they'll tell me is, I've had like 10 people come talk to me, and I don't understand what any of them are talking about. And they all have different ways that they do things, and none of it makes sense. And I think that and most of them say, I think that it's just too risky right now to be part of it. And so they just, yeah, at least the farmers that I've talked to.
Well, we could keep Richard up here all day, but let's thank him for speaking. If you want to keep him up for all day, he'll still be here for a while to ask questions. Otherwise, his office is just not far away from here, and you should go talk to him sometime. And I apologize for people who did not get to ask questions. I should have answered you, but thank you all very much. And next week we have another seminar. I will send an update about that. I think it's Mr. Cook's, isn't it? Yeah, excellent. Michael Cook. So I'll send a note about that. Thank you all very much.